Good afternoon or good morning to you. Welcome to Chapter 4, our Global Climates and Biomes unit. Now, this ed puzzle, I'm going to try to go through it as quickly and as thoroughly as possible, but it's got a lot of sides. Buckle up, because a lot of things we cover are going to build on throughout the year, and they build on each other. So pay attention, take some good notes, and let's get into it. First things first, as we get into Unit 4, we want to talk about the main difference between weather versus climate. And really, kind of the main distinction between weather versus climate is we're going to be looking at time scales. Weather is happening on a short time scale. So what is the weather right now? What is the weather going to be like tomorrow is usually what we're talking about. So what is happening within this right second, or what's happening general to the day? Is it raining? Is it snowing? Is it hailing? So short term. On the other hand, climate is going to be the average trend of an area. So over decades, really. So when we're thinking about the average type of temperature, the average type of weather, is this an area that typically snows a lot? Is this an area that's prone to tornadoes and hail? When we get into climate, that's going to help us also distinguish what biome an area is attributed to. Is this a tropical rainforest? Is this a Sahara desert? What kind of biome is this based on the typical climate it has? What is my overall trend that I'm seeing in the area based on its weather and climate? And that can help us attribute that biome. But we'll get into biomes later on as we get into this unit. The climate of an area is going to be really driven by five main factors. And this is going to look at our temperature and precipitation patterns. We look at the average temperature precipitation patterns for an area, and then that's going to help us kind of determine what is the climate. So that temperature precipitation pattern is going to be driven by these five main things. We're going to get into each of these in depth in this exact order. So take note of it. We're going to be looking at first the unequal heating of the Earth by the sun. Then we'll talk about atmospheric convection currents, the rotation of the Earth, and the Coriolis effect. How does that Earth's orbit around the sun on a tilted axis also attribute to temperature and precipitation patterns? And finally, we'll talk about, of all things, ocean currents, because yes, our oceans also tie into our weather and climate. So let's first talk about the atmosphere and talk about the unequal heating of the Earth. Before we talk really more about that unequal heating of the Earth, the first thing you got to understand is the atmosphere. There's five main layers of the atmosphere. Really, the first two are going to be the ones we talk about the most, the troposphere and the stratosphere. And these are really going to come in when we talk about air pollution. But we also have, after the troposphere and the stratosphere, we'll also have the mesosphere, the thermosphere, and the exosphere. As we're going from the Earth's surface and we're going upwards throughout each of my layers, we're going to be decreasing in density, okay? So we're also decreasing in pressure. You might think about how if people ever go hiking in the Himalayan mountains, sometimes, or if they're trying to do Mount Everest, they'll have to have oxygen with them because the air is so thin as we go higher, and that's because the density and pressure of that air is decreasing as we go up, which we can see here on our graph. Also, temperature is also going to be decreasing as well. We'll talk about why that makes sense in a little bit. The way that I always remember it, you can think, I just think T-Rex says memorize this early. And I do T-Rex to remember TR for troposphere, this as in TH thermosphere. But it is important to know these five distinct layers. The stratosphere also has a sublayer known as the ozone, and the ozone really happens right between the troposphere, which is where we are. The troposphere is what we're breathing in. The stratosphere is right above us, where we have like all of our clouds and our weather patterns forming. And the ozone is right sandwiched between them. Usually we attribute the ozone as the lower part of the troposphere, the lower part of the stratosphere. But we'll be talking more about that as we get closer to why the stratosphere and the ozone layer is so important to be blocking the Earth's from those UV rays from coming in from the sun. But we'll talk about all those exciting things as we get into air pollution later on this semester. Okay, as promised, one of the main factors, and I apologize, my face is always in the way. One of the main factors that is affecting the temperature and climate of an area is going to be unequal heating of the Earth. We'll have a good graphic showing this in just a second, but as the Earth receives solar energy from the sun, it's going to receive them in different amounts depending on where we are at the sun, okay? it's going to affect us in two different ways. And I feel like I'm a visual person, so I'm going to real quick flip over to the next slide. That way we can see that there's unequal heating of the Earth from the sun solar energy. Okay, hopefully this visualizes it a little bit more, and then we're going to talk through this. So there's two main reasons, and they're up here. Maybe take note of them, of why we have unequal heating of the Earth, even though the Earth is equidistant from the sun. Well, one, there's variation in the angle the sun rays strike. If I'm looking at this, and we'll get through this when we talk about our weather and climate labs, but depending on the angle at which that solar energy is coming in this way, hitting the Earth, and depending on where we hit it along the Earth, that's going to affect how much of the solar energy per area is receiving on the Earth. So if it's heading right here at the perpendicular area, I have the smallest area of light coming in from solar energy. Because it's a small amount of area, but it's still the full amount of solar energy, that means that it's getting most of the solar energy or most intense energy coming in at a perpendicular angle. Whereas if I'm at an oblique angle, if I'm hitting it at a tangent up here, it's the same amount of solar energy, but that solar energy is now spread out over a larger area. And we'll map this out in our labs coming up this week, our weather and climate labs. But as that solar energy comes in, because it's now being spread over a greater amount of area due to the angle, it's the same amount of energy, but spread out over a greater space. And so that means that it's less solar energy received per square kilometer or square meter, whatever your unit of measurement is. So the more perpendicular it is, the smaller the area that's being hit, which means it's getting more direct, more intense sunlight, solar energy there. Whereas at the oblique areas, it's hitting at a greater area. That same amount of energy is being dispersed or spread out over a greater area. So then that means it's less solar energy at each one of these points. So that's the variation in angle. And also that kind of ties into the amount of surface area in which it's distributed. The angle also comes in, it talks about it right here. When we're coming in at an oblique angle, there's also more atmospheric layers we have to pass through. As solar radiation passes through layers of the atmosphere, it's going to decrease. It's going to be distributed and losing some of that solar energy the more atmosphere I have to pass through. So that's another reason here at the polar areas, because the sun rays has to travel through more of this atmosphere right here, that's going to lose solar energy, and so less solar energy is hitting. And when it does hit, it's spread out over a greater area of land. So those two reasons kind of tying in together is why some areas, such as my equatorial tropic regions are going to be receiving more solar energy, heated up more from the sun versus my polar exterior regions. I know this is kind of a lot, so don't worry. As I said, all of these concepts we'll be exploring in class. Okay, so let's keep going. In addition to the unequal heating of the Earth's surface that occurs due to incoming solar radiation, also known as insolation, incoming solar radiation, we also have something known as albedo. Albedo is a vocabulary term you should be familiar with, which is the percentage of incoming sunlight that is being reflected from the Earth's surface. The greater the albedo, the less warm it's going to be, because if more energy is being reflected off, then that means I have less heat being trapped on the Earth's surface. So areas that have low albedo are usually going to be darker areas, such as concrete pavement, forests, which have a lot of dark greenery, asphalt. These have very, very low albedo. And if I have low albedo, that means I have low amounts of solar radiation being reflected off of the Earth's surface. And that means that a lot of that solar radiation is being kept and retained here on the Earth's surface. So areas that are equatorial, that have like tropical rainforests, that have a lot of grassland, that have a lot of construction and urbanization, these are going to be warmer areas as compared to my polar regions that have a lot more lighter colors, such as water, sea, and ice. These numbers are going to be way higher because if there's a lot of higher numbers, that means we have a lot more of that radiation being reflected off of the Earth's surface. Less heat being retained means that the temperature overall is going to be cooler because that solar energy is being reflected off. We also want to know a little bit about Earth's air currents as well. There's 4 things kind of going on that you should be familiar with. And the next couple of slides, I hope will make a little bit more sense if you know these 4 properties before getting into them, because it can get a little confusing sometimes when thinking about properties of air. First of all, air property known as density, less dense air rises. That also ends up being warm air as well. So you might think, like, if you're ever on 2 bunk beds, like if you're on the hot bunk bed, the top one, it always gets really hot, versus the cool one, because that warm air rises. Warm, less dense air rises, dense, thicker air sinks. So think also about our layers of the atmosphere. We have the denser layers at the bottom, and as we go up, my pressure and my density are going to decrease as I go higher and higher up the Earth's atmosphere. You should also know that in terms of water vapor capacity, warmer air that's up higher is going to have a higher capacity for water vapor than cool air. That's why we usually see that cloud formation way up high in the stratosphere above us where we are. We're in the troposphere. So those clouds are going to form up higher because that warm air has a higher capacity for containing that water vapor. You should also be familiar, this is probably a newer term for you, adiabatic heating and cooling. And I probably am saying that completely wrong, but that's how I've always pronounced it, adiabatic. So in adiabatic heating, air rises in the atmosphere. And when it happens, remember, warm air rises, but also we have lower or decreasing pressure as we rise up. So as that warm air rises, the pressure is going to decrease. The air is going to expand. We're increasing volume, and it's going to cool off because I have greater amount of space between my air particles. And then once it cools off, cool air sinks. That cool air is going to come down. As that cool air goes down, my pressure is also increasing. We're becoming thicker, more pressure down here. The air is going to decrease in volume, concentrating the space between the particles and also warm up that air as well. So we have rising, cooling, coming down, warming. We'll talk about that more on the next slide. Also thinking about how if solar radiation is needed to turn my liquid surface water into water vapor in the form of evaporation, so energy comes down, turns it from liquid into a gas, that gas then rises. When that gas condenses and turns back into a liquid in the form of water vapor, or in precipitation in my clouds, that is also going to release energy. So if it took energy to go from liquid to gas, going from gas to liquid is going to release that energy. We call this latent heat release. The air is then going to warm as that energy is released up there, up high in the sky with the clouds. And then that's going to cause our water and our precipitation to rise further. That warm air is going to continue rising. All these 4 properties are going to be explained a little bit more in the next slide. So hold on. So what happens is because I'm having this unequal heating of the Earth and all these properties that air has between density and water vapor capacity, we're going to form atmospheric convection currents. So think back when we were talking about the layers of the Earth, we had the mantle, and in the mantle, especially in that asthenosphere, we had those convection currents, warm, rising, cool, sinking. Well, we're going to have atmospheric convection currents as well. In particular, the 2 that you should be or will become familiar with are Hadley cells and polar cells. Hadley cells and polar cells really kind of interact in very similar ways. They're just at different locations. Our Hadley cells are going to be happening right at the equator and the Tropic of Cancer, Tropic of Capricorn, 30 degrees north and south of that equator. Our polar cells are going to happen way up at the top and the bottom of the Earth's atmosphere. We'll talk a little bit about the ITC, the Intertropical Convergence Zone, which is the area of Earth that receives the most intense sunlight and where we're going to see those Hadley cells form. Promise visuals coming right now. Okay, so here are my Hadley cells. This is also one of our instances of convection currents, warm air rising, cool air sinking. So let's talk through it. Here is my ITZ, my Intertropical Convergence Zone. This is right here at the equator. This area is receiving the most amount of the sun's incoming radiation, right? Because it's right perpendicular. So as the sun hits this area, we've got a lot of water vapor here. So what's going to happen is the first thing is that the sun is going to heat this moist tropical air, causing it to rise. Warm air rises, right? As it's rising, we're going to have that adiabatic cooling, which is whenever it causes my particles to increase in space, and that's going to cause that water vapor fall down. When that happens, we're going to have this latent heat release. Remember, as we go from gas into liquid, we have that release of energy. Heat and there's that form of energy that is released, which causes my cloud to rise up higher because I'm having more and more warm air in my system as we go from gas into liquid in the process of condensation. So my cloud forms, gas turns to liquid, releases heat energy, that warm air continues to rise. When this warm air rises, it's going to push away and kind of be like, move it out of the way. Cold air that's way up above it. Warm air rises, so as it comes up, it's going to push away this cool air. The displaced cool air is then it comes down. As it comes down, it's been experiencing increasing pressure as it's getting closer and closer to the Earth's surface. As it increases pressure, it's going to increase heat, increase that energy. This is our adiabatic heating. And as it warms, then it's going to pick up that moisture, and then the cycle is going to continue again. Most amount of heat causes evaporation, brings up that cloud, latent heat release pushes it up higher. We displace that cold air. The cold air comes down, warming as it gets closer and closer to the Earth's surface, and then we keep going again. These are my Hadley cells. Something very similar is also happening at my polar cells as well, which we're going to see in just a second. But don't worry, we'll talk about this more in class, and you'll also explore this in our Earth system, or excuse me, our weather and climate station labs. So, oh, my face is kind of in the way. There we go. So, Earth's rotation and the Coriolis effect. Coriolis effect, Earth's rotation, and that thing we just talked about, the Hadley cells convection currents. All three of those are going to come together to form my Earth's currents, all the wind patterns around my world, which we're going to get to. I promise. I feel like it's like a whole bunch of puzzle pieces, but I swear they're all going to come together in just a second. Earth's rotation, as the Earth rotates, and we're going to be rotating in, if you're looking at it from above, this is a counterclockwise way. So we're going from west to east, west to east, west to east. As the Earth rotates, we're going to be deflecting our wind. So my atmospheric wind currents, which are displaced above the Earth, as the Earth turns, we're going to have a displacement or a movement of that wind, of their atmospheric currents, known as the Coriolis effect. So what this is kind of demonstrating here, and we'll talk about this in class as well, is that if I were to throw a ball straight from the North Pole and I try to throw it in a straight line, the actual path of the ball is going to be going at a skewed angle because of this Coriolis effect. Because as the ball is airborne and the Earth is moving below it, when it actually lands, it's going to be happening at a distance that is not in a straight line from where that ball was thrown. The same thing is happening with my airborne, my atmospheric wind currents. Wind currents are airborne, but as the Earth turns, we're going to have this deflection, this movement that is different from where it originally started. I'm going to come back to this slide, I promise. I just want to kind of, I'm a visual person, so sometimes I feel like it's easier to see. So what we're thinking about is right here. My wind is going to be deflected to the left because my Earth is turning to the right. So what's happening is my Earth is spinning from west to east, west to east. My Hadley cells at the equator is causing that warm air to rise. The rising warm air is then deflected because of this Coriolis effect, because the Earth is spinning below it. So what ends up happening is we kind of get like a pulling or a dragging of my wind currents to the west as my Earth spins to the east. This can all be explained, this is the second slide, by the Coriolis effect, which is the deflection of an object's path or atmospheric currents due to the Earth's rotation that's happening below it. Prevailing winds of the world are going to be kind of a mixture of those Hadley cells, like convection currents, warm air rising, cool air sinking, warm air rising, cool air sinking, and then also that Earth's rotation causing this Coriolis effect and all these global wind patterns. I did want to point out real quick, these are also my polar cells, kind of similar to my Hadley cells where I've got that warm air rising and being deflected. And my polar regions, these are just happening from the 60 to 90 degrees on the latitude spectrum. Hang in there, we're doing great. Okay, this one hopefully is a little bit more familiar. Did you know that seasons are caused by the tilt of the Earth's axis? Oh my gosh, Earth's axis of rotation. So the Earth is actually tilted at 23.5 degrees. So if we think about the differential heating of the Earth based on the incoming solar radiation, in contrast to what's happening with the incoming solar radiation, that's going to cause our seasons. So let's look at a picture of that. All right. So we have a March and a September equinox. And at the March and September equinox, due to the tilted axis and where that incoming solar radiation, where roughly every single part of the world is receiving exactly 12 hours of daylight. Every part of the world is receiving the same amount of sunlight because the March equinox and the September equinox are the two times of the year when the incoming solar radiation from the sun is hitting right at a perpendicular angle along the Earth's surface. Any other time besides that, we're getting a differential heating. So from March until June, so my kind of summer months, you guys know the days are longer because my northern hemisphere is going to be getting a lot more of that sunshine. So that's why we have summer, is because we're getting more sunlight. Here's my equator here in white. So we're getting a lot more sunshine in the northern hemisphere from March until June. But when we get to September through December, September into December, now we're getting more and more of the world in the southern hemisphere is receiving more of that incoming solar radiation. Here's my equator, more of it's hitting that Tropic of Capricorn, which is below the equator. So that's why in the southern hemisphere, the southern parts of the world, they have their winter when we have our summer, because they're going to actually have warmer weather when we have colder weather. And it's because of this differential incoming solar radiation due to the tilt of the Earth's axis. So depending on the patterns of how much radiation is coming in and hitting my surface, that's going to tell me what season or the prevailing weather patterns of an area at a given point in time. All right. We're now going to get into ocean currents. We'll talk a little bit about ocean currents, and then finally we'll talk about rain shadow, El Nino, and then we're done. So hang in there. We're going to try to get through this as best we can. Ocean currents is that fifth property that I told you guys that you needed to know about that's going to be driving our climates. Ocean currents is kind of a combination of that incoming solar radiation. It's going to be tying in salinity, how much salt, Coriolis effect, location, whole bunch of things. The good news is that the overall movement of ocean currents is very similar to air currents, right? Warm air and warm water are both going to rise and expand. Cold water, just like cold air, is going to decrease, fall, become more compact, and cool down. So warm water rises, cool water falls. That's something nice. We're going to call this overall pattern of movement of our ocean currents are known as gyres. Some people say gyres, tomato, tomato, potato. As we have these large-scale water circulation patterns moving all these nutrients around my ecosystems, all around my planet, they're going to be called these gyres, which are the overall prevailing movements. Okay. Wow. Who knew that there's so much happening right underneath the surface of our oceans? These are our oceanic circulation patterns. We have our warm air, or excuse me, we're talking about water now, ocean current. We have my warm water located in red. So these are going to be higher up, closer to the Earth's surface, closer to that water surface. And then I have my dark blue arrows, which are notating all of my cooler, denser water that's going to be below that. We also have something notated in these kind of shaded areas. These are called my upwelling zones. My upwelling zones, I'm going to give you guys a slide that gives you actually text for this, but my upwelling zones are going to be areas where as ocean currents hit it, the ocean currents hit the western side of continents, diverge, and as that cool air diverges, it makes room for warm water to rise. That warm water then rises, and it's going to be bringing all these nutrients that are needed by our photosynthesizers, my aquatic plants. It's going to bring up all these nutrients from below, way down at the deep depths of the ocean, and going to be giving all this nourishment to my surface level organisms. So let's give you guys some context on that. We call this again upwelling. Upwelling is going to be ocean surfaces currents diverting, deeper waters rise and warm, kind of similar to that adiabatic heating and cooling. I mean, whenever it comes up, it's going to have that water displacement. The upward movement is going to be bringing nutrients down from the ocean's bottom, supporting all my producers, okay? And this usually is going to be happening along the western side of my continents, this upwelling or bringing up of nutrients as we have our surface currents diverging. I'm so sorry. My words are just, I feel like my words are never working, but in particular, they're really not working today. So here we're going to break up the words with a little joke. This kid's so freaking cute. Look at him. Oh, and he's got little parrots on his shirt. I just noticed that. Oh, what a kid. Okay. Another thing that's going to be happening in my oceanic currents is something called thermohaline circulation. If we break down that word, because that's kind of a crazy word, thermo meaning heat or temperature, haline is a fancy word for salt. So I'm talking about warm and salt, or temperature and salt circulation. This is another pattern of oceanic current circulation that's going to be driving the forces of how my ocean currents actually go through my entire world. This is a very crucial process, and let's talk about what's happening with it. But we're going to be talking about ocean currents that have a lot of salt. This is a lot of words. I'm going to kind of, okay. I like to do graphics first. I apologize that that graphic wasn't first. We'll go back to that slide once more. Warm water rises, cold air sinks. Cold water, I keep saying the wrong thing. Cold water sinks, warm water rises. In addition, salty water is denser. Salty, dense water is also cold. So we have this deep currents that are happening way below the surface of the water that are salty, and they're also cold. Cold, salty below, warm waters at the top. What happens though is, let's kind of start it from the Gulf of Mexico here. At the Gulf of Mexico, we're kind of near the equator right here. And so we're going to have some warming. The warm water is going to be rising. It's going to be flowing along the western coast of Europe. As my warm water from the Gulf of Mexico goes up north, goes closer to my polar regions, it's going to cool. We're not receiving as much incoming solar radiation. So as that ocean water cools, it's going to sink down deep. And as it gets down deep, it's going to get salty, it's going to be freezing, and it's going to be denser, and it's going to be traveling below, way down in the depths, deep, dark of my ocean currents. As it's doing this, it's going to be connecting all my ocean surfaces, circulating nutrients, circulating all these rich materials and minerals that are needed. And this process can take hundreds of years. It can take decades. It takes a really long time for one particle of water to make its way all the way through the thermohaline circulation. My deep cold current eventually makes its way back to the equator. When it makes it back up to the equator, we're going to be experiencing heating, more incoming solar radiation here in my equatorial regions. As the water then heats up, it's going to rise up, circulating up. It's now warmer, more shallow water, and it's going to circulate back through, connecting all my world's oceans. Here's that text that kind of contextualizes what's all going on. Gulf of Mexico makes its way up to the North Atlantic. It's going to make its way to the polar regions, freezing, evaporating. As that water evaporates, the concentration of salt is going to intensify, making it denser, making it sink down. Cold, salty water is dense. It sinks to the bottom of the ocean, goes down deep with my deep ocean currents, and it's going to be moving all the way through until it reaches the equatorial regions again, heating up, going back up to the surface, becoming more shallow, and circulating back through to that Gulf of Mexico once again. Thermohaline circulation. If you're like, what in the world is going on? This is why we're doing hands-on stations. Our weather and climate stations labs will hopefully help kind of visualize all of these processes. Okay, dokie. What's actually really cool is that, remember we talked on the very beginning, we had 5 processes that are affecting weather and climate. We said ocean currents is a way that can affect weather and climate, but you might be thinking, wait a minute, ocean currents is below the surface, it's underwater. Weather and climate is usually above the water, on the land masses. Well, because of the Earth's oceanic currents, and because of this heating and cooling of these ocean currents, we can actually affect the temperature and the climate of nearby land masses. For example, at the same latitude, we have Newfoundland, Canada, and England, but England's winter temperature, due to this thermohaline circulation, is actually going to be 20 or 36 degrees Fahrenheit warmer than in Canada, even though they're at the exact same latitude. Again, looking at the differences between where do we find Canada, I actually don't know where Newfoundland is. It's somewhere over here in Canada versus England, which is right there against that thermohaline circulation when I have that warm, more shallow water hitting that coast of England. Kind of cool stuff. Oh my gosh, we're almost done because we're getting to the joke. A pregnant bar walks into a boba shop. She says, I'll take an almond milk tea, extra sweet with boba, which is so good. Cashier says, why the big pause? Panda says, I'm not sure I was born with them. All right, woo! We have two last concepts. We're going to talk a little bit about El Nino, also known as the ENSO, El Nino Southern Oscillation, ENSO, the ENSO. We'll talk about rain shadows, and then we're done with chapter 4. Okay, thinking back to our atmospheric convection currents. These are my Hadley cells. This is right here at the equator. We set it in my Hadley cells because the Earth is rotating from west to east, but I'm having some rising of my atmospheric convection currents because it's warm here at the equator. We have a deflection due to the Coriolis effect. 9 times out of 10, or maybe it's actually a different fraction than that, but most of the time, I have what's known as my trade winds, which are going to be pushing my surface water. It's going to be pushing my air from east to west, which is the opposite direction of the Earth's rotation, which, if we think about it, makes sense because we have this happening. So we're talking about what's happening right here off the coast of Peru, okay, in South America. Okay, that's what happens most of the time. However, we have something known as an El Nino year every 3 to 7 years. So every once in a while, this is going to happen where the trade winds are going to weaken. If the trade winds are weaker, then actually these winds, these atmospheric currents are going to be pulled along with the natural rotation of the Earth's surface because they're not rising as high. We're not having as much. And so what's going to happen is as my winds are now flowing from west to east, we're pushing that warmer air now towards South America. We're also bringing in lots of surface water as well, this warm surface water hitting along the western coast of South America. And what this ends up happening is we end up having a warmer year for South America. It's usually also bringing in that cold water, so it's a little bit more dry. But we also have a lot of differences in the weather and the climate of the region in these kind of freak El Nino years in comparison to the normal ones whenever we're pushing those winds towards the coast of Australia. Contextualizing what we just saw in that picture, the trade winds are going to be weakening. So instead of going from east to west, now we're going from west to east. We're pushing all of that now towards the west coast of South America, pushing it towards that area over there. The movement of the warm water and the warm air to South America then is going to be producing drier, wetter conditions. That is an oxymoron, drier, wetter conditions. Let me double check on that. And I'll address that in class because I feel like whoever wrote this PowerPoint, I don't really love that. It's also going to be decreasing productivity there and our fish populations because we're bringing in all this, we're suppressing the upwelling because if it's warm water, instead of that cold water rising up, remember bringing up in that upwelling, the bringing up of the nutrients from the bottom. So if I have warm air there, it's going to not allow that cold water to rise up, bringing those nutrients. So it's decreasing productivity in this area. We call these El Nino Southern Oscillations, also known as ENSO, every 3 to 7 years. Oh my gosh, last concept is rain shadows. And I know we're going wrong on time. There's a lot of slides for this one. Rain shadows, what happens is having all this precipitation coming in off the coast, coming in and hitting my land masses from the ocean. As that happens, my water vapor is going to hit the side of a mountain, what we call the windward side of the mountain, because it's where the wind is hitting the side of the mountain. Windward, okay. So as that happens, we're essentially hitting a physical barrier. And as that water vapor hits the side of the mountain, it's going to cause that precipitation to fall right there. And so on the windward side of the mountain, we have lots of precipitation. And so because of that, we're going to have lots of dense vegetation on this side. Then once that warm air has displaced all of the precipitation on the windward side, it's now going to travel to the other side, or it's going to experience adiabatic heating. It's going to be coming down as it decreases in altitude. As we decrease altitude, we're getting closer to the Earth's surface. Getting closer to the Earth's surface means that we have an increase in pressure, increase in the heat of that area. And so we have this dry, warm air coming down what we call the leeward side, which is the opposite side of the mountain. And I have a visual for this. And so what we end up having is called a rain shadow, where we have drier, more arid conditions on the other side of the mountain that is not facing the coast. So here is kind of a graphic to demonstrate that. Again, I've got my evaporation happening here. I have my warm oceanic currents. That's going to cause precipitation. Precipitation comes inland onto the coast and hits what's called the windward side. Because we have a physical barrier, the windward side is going to cause a drop or a release of that precipitation. There's lots of rainfall in this area, which means we're going to have moist, dense precipitation, vegetation, not precipitation, dense, moist vegetation. Then that air is going to continue onto the other side of the mountain. As it does so, it's going to experience adiabatic heating. It's going to come down. As it comes down, it's going to get warmer and warmer as that pressure increases once more. So we have this dry, warm, arid, almost kind of like a desert on the other side, what we call the leeward side of the mountain. You made it to the last slide. Our riddle for today: who makes it has no need of it. Who buys it has no use for it. Who uses it can neither see nor feel it. What could it be? Ha, ha, ha. You made it to the end of a very long ed puzzle. I'm not going to keep you guys very much longer. I just want to say you're awesome. Thank you so much, and I will see you guys in class. Thank you.